I have the pleasure of introducing Brad Sturt today. Brad is at the University of Illinois at Chicago, which when I was in Chicago was called Chicago Circle. I don't know when that changed. He did his graduate work at MIT in operations research. And I first met Brad, the only time I've actually met him in person was a few months ago at the Election Verification Network conference in DC. And he gave a presentation on really an optimization problem that uses a lot of combinatorics that I was completely unaware of, and its import in making election testing more practical. So it's really interesting combinatorial work, and I'm interested in seeing more, and I hope others will be as well. And I'm going to turn it over and let Brad introduce the problem and get started. So welcome.
Thanks. Thanks so much, Josh, for this invitation. It's a pleasure to meet all of you. And I just want to note that Josh and I met actually a year ago prior to that, but I wasn't memorable enough. But yes, it was a wonderful.
Yes, I do remember. Yes, you're right. Thank you. I'm sorry.
No, it's all good. And so anyway, it's a pleasure to be here. As Josh mentioned, I'm an assistant professor of operations research at University of Illinois in Chicago. And for the past 2 years or so, I've been working on using my area of research, which is mathematical optimization, to improve security and public confidence in vote counting. And so that's the work I want to present today. This has already been a little impactful. The tools that I'm going to talk about have been deployed in several real-world elections in the state of Michigan over this past year. And I think it's pretty exciting, bridges some different technical areas. So there's a preprint online of this work with this title. This is work with Alex Halderman, who's a professor at University of Michigan, and Braden Crimmins, who's a PhD student in CS at Michigan and simultaneously a law student at Stanford. All right, so let's begin with a crash course on US elections. 93% of voters in US elections use paper ballots. And they vote using paper ballots in a variety of different ways. This includes marking a paper ballot at a polling location in person. It includes ballot marking using a ballot marking device that then prints out a paper receipt, and as well as includes hand-marked paper ballots that are mailed in. These paper ballots, when they're filled out, are then scanned and tabulated using voting machines at the precinct, though it varies a bit depending on where you are in the country of where those machines are. And then when the election is over, those machines print a poll tape, basically just like a grocery store receipt with a vote total for each candidate. And this whole system, obviously greatly simplified of how this works, but seeing this flow diagram begs a very natural question, which is, why do we use voting machines to scan and tabulate votes in the US? And the reason is that ballots in the US and some other countries have a huge number of contests. So this is an example of a typical ballot. This was from St. Louis at November 2020. This ballot has more than 30 contests, ranging from things such as voting for senator to voting for local school board. And within each contest has many different candidates. Because there are so many contests on a ballot, it's often cost prohibitive and time consuming, among other reasons, to do hand counting. And that is a reason that we use these voting machines. So as many of you who've worked in this area or just have been around for the past decade or so are aware, there's been much voter distrust in United States elections, and including the coverage of elections in popular media. And some of this concern has concerned these machines that scan ballots and count votes. And to understand why there's controversy concerning these machines, we must understand just a little bit about how these machines work. So for a voting machine to count votes accurately, it must be configured before an election with a correct mapping between the voting targets on the ballot. By voting target, I mean that little bubble or oval next to candidates that you fill out. There must be a correct mapping between those targets on the ballot and the candidates who should receive the votes when that target is marked. If a voting machine is configured with an incorrect mapping, accidentally or intentionally, then the machine may count votes for the wrong candidates. And voting machine misconfigurations has lied at the source of much of voter distrust and issues with elections in the US. So how can misconfigurations of voting machines be detected prior to elections? Well, the most common tool today that's used for accomplishing this is a procedure that's called logic and accuracy testing. So what is logic and accuracy testing? Logic and accuracy testing, I'll sometimes abbreviate it as LNA testing, is a testing procedure that's required by law in all 50 states prior to each election. The goal of LNA testing is for election officials, roughly speaking, to verify that the voting machines work correctly before the election takes place. That's the goal. The procedure is very simple. It consists of election officials filling out some different ballots in some different ways, feeding them into each voting machine, and then checking, clicking print, and then checking to see if the machine outputs the correct totals for each of the candidates on all of the from the ballots. And this procedure has been around for over a century. It dates back to the mechanical lever machines, like I've shown here, from the post-industrial revolution. And LNA testing was originally designed to ensure that the gears in those mechanical machines advance properly. So to say what I just said a moment ago, but as a flow diagram, LNA testing goes through this following procedure. So before the election takes place, the officials first configure the election equipment. They then, during LNA testing, choose some heuristic by which they're going to fill out the ballots in a stack of blank ballots. They then fill them out, feed the ballots, that stack they call the test stack, into the machine. The machine outputs the vote totals. If those vote totals are correct, the machine gets used in the election. If they're incorrect, well, first they make sure they check whether people filled out the test stack correctly. And then if it still is incorrect, then the machine gets investigated. So to understand what LNA does and what it doesn't do, let's consider the following example of a very simple election comprised of two contests. So in this toy election, the first contest is a presidential contest with three candidates, Washington, Jefferson, and Lincoln. And the second contest is a Senate contest with candidates Webster and Clay. In both contests, let's say a voter is allowed to select up to one candidate. And in this slide, I've shown an example of a test deck for this election comprised of 6 ballots. And this test deck in particular satisfies the most stringent requirements currently in place by any state. Namely, it's required in about 17 states, which is that the test deck must give a different number of votes to each candidate, all the candidates within the same contest. So more specifically, in this test deck, we observe that the first ballot gives a vote for Washington and Webster. The second 2 ballots at the top in this test deck each give votes for Jefferson and Clay. And the final 3 ballots on the bottom each give a vote for Lincoln. So if this machine was configured properly, then this test deck is fed into the machine would output this vote totals. Namely, 1 vote for Washington, 2 for Jefferson, 3 for Lincoln, 1 for Webster, 2 for Clay. And as you see, these are different vote totals for the presidential candidates as well as for the Senate contest. I think I saw a question.
Yeah, I was just wondering, is there no concern about mixing up between the presidential and Senate candidates? Why does it have to not be unique over the whole ballot?
You are exactly 4 slides ahead. I'll get to that in a moment. But what I'm saying right now is not how they should do it. I'm saying this is a test deck that is satisfying what is currently the strictest, most stringent requirements in any state with regards to giving a variety of different things. Namely, this is a test deck that has a property that every candidate within the same contest receives a different number of votes. So before we critique this test deck, let's just see what this test deck would detect. So let's consider some examples. So as our first example, let's suppose that the machine was misconfigured such that the target next to Washington is interpreted as a vote for candidate Jefferson. The target next to Jefferson is interpreted as votes for Lincoln, and the target next to Lincoln is interpreted as votes for Washington. So if the machine was misconfigured in that way, and watch closely at this test deck, this is how the machine would interpret it. So I'm just going to flip back and forth a couple times. So you see here that the original vote for Washington was interpreted by the machine as a vote for Jefferson. The 2 for Jefferson are interpreted as votes for Lincoln. The 3 for Lincoln at the bottom interpreted as votes for Washington. Given that interpretation, the machine would output these vote totals. A human would look at these vote totals and see that Washington, Jefferson, Lincoln are getting the incorrect vote totals. And so this misconfiguration, shown on the left, would be detected in LNA testing by this test deck. Let's see another example. So suppose, for instance, that the votes for Lincoln and Clay were swapped. In that case, looking again closely at this test deck, this is how the test deck would be interpreted. So looking in particular at these second and third ballots on the top, we see the votes for Clay get moved up and interpreted as votes for Lincoln. Well, these voting machines are configured such that if there is an overvote in a contest, meaning if more candidates are selected in a contest than is allowed, in this case only one candidate is allowed to be voted on in a presidential contest, then the machine interprets it as if no votes were counted in that contest. So given this test deck, under the machine will output 0 votes for Jefferson, 0 for Lincoln, because in all the ballots for which there was a vote for either Jefferson and Lincoln, it included votes and the machine interpreted those ballots as having votes for both. They're overvoted, therefore counts as 0. And also the Lincolns got interpreted for Clay. So these vote totals are incorrect. So this misconfiguration would be detected by LNA testing with our test deck. And now to Melissa's point before. This is the third final example. Let's suppose that the machine was misconfigured such that votes for Jefferson and Clay were swapped. Looking at our original test deck, this is how it would be interpreted by the machine. I'm just going to flip back and forth a couple of times. And what we observe is that every time Jefferson and Clay were got a vote, they got a vote on the same ballot. So the machine, even though it was misconfigured, would interpret these second, third ballots the same way, leading to the correct output. So this example of a misconfiguration would not be detected by this test deck. And more generally, this example illustrates that even test decks that satisfy the most stringent state requirements currently in practice are not guaranteed to detect all misconfiguration-based swaps. Okay, fine. But are misconfigurations of machines, in particular those that swap votes between candidates across contests, is this a realistic threat? Is this something that we should be concerned about? To answer that, let's go through some examples. So first, let's rewind to Antrim County, Michigan in the 2020 general election. So in this election, voting machines were accidentally misconfigured with mappings that caused votes for Republicans to be tallied for Democrats and votes for Democrats to go uncounted. Oops. This incident didn't cause votes to be swapped across contests, but it shows how accidental misconfigurations can indeed cause votes to be swapped. And this type of an accidental misconfiguration was not a one-off incident. There are a number of examples I can cite for which similar things occurred, such as DeKalb County, Georgia in 2022. And in these sorts of examples that I've mentioned thus far, these accidental misconfigurations that cause votes to be swapped across candidates, they were quickly caught and corrected after the election. However, these misconfigurations resulted in the initial publication of incorrect vote totals and generated significant negative publicity, which in turn harmed public trust. And because these sorts of misconfigurations happen reasonably frequently, let's see an example from 8 months ago. So in November of 2023, in Northampton, Pennsylvania, voting machines were misconfigured to accidentally misconfigured to swap votes across two contests. This was across two judge contests, yes, no, of whether to retain two different judges. This led, in this case, to a huge amount of voter confusion on voting day, as well as long lines. So, given all of this, we face our question here, which is, can we modify LNA testing? Can we use it somehow to catch these types of misconfigurations, namely those that could swap candidates not only within contests, but also across? So as our first attempt at answering this, I want to show an idea that would work, but the idea is a really bad one. And I'll explain why in a bit. So the first idea, and in particular an idea that would work, would be to give a different number of votes to every candidate in every contest. What do I mean by that? Well, recall for our simple example before, this was our previous test deck, and this on the right here would be a test deck that gives a different number of votes to every candidate across every contest. Namely, this test deck would give 1 vote for Washington, 2 for Jefferson, 3 for Lincoln, and then 4 for Webster and 5 for Clay. And so the previous test deck, if we recall, will detect swaps between candidates only within the same contest. And this simple heuristic, this one on the right, would detect swaps between candidates within and across contests. However, I said this was a bad idea. Why is this simple solution a bad idea? Well, our original test deck required only 6 ballots. This new test deck requires 9 ballots. And the issue now becomes a practical one, which is that the difficulty and cost to election officials of performing logic and accuracy testing grows with the length of test decks. Moreover, what we've seen on the slides here is a simple example with only 2 contests. In real-world elections, there are many contests and 100 or more often candidates. And so the simple idea of giving a different number of votes to all candidates quickly becomes completely impractical. And here is our what we have done. So what is our approach? So we've developed in this research an algorithm based on mixed integer linear programming for finding minimum length test decks that are mathematically guaranteed to detect any misconfiguration that swaps votes between candidates. Said another way, we've developed an approach that finds test decks that are guaranteed to give the incorrect output if a machine is misconfigured to swap votes between candidates within or across contests. It'll detect it either because the misconfiguration would cause a swap of candidates with different numbers of votes, or because the misconfiguration would cause an overvote in at least one contest in at least one ballot. And out of all test decks with this mathematical property, our algorithm outputs a test deck with the fewest number of ballots in order to ensure practicality. And let me show you, before getting into the technical part of the talk, let me show you what the output of our algorithm looks like. So recall, this was the previous test deck. And this is a test deck output by our approach. Now, if you look at it closely, it looks pretty similar to the original one. It still gives 1 vote to Jefferson, 2 to Lincoln, 1 to Washington, 2 to Jefferson, 3 to Lincoln, 1 to Webster, and 2 to Clay. Just like before, it still involves 6 ballots. However, one can verify that if a voting machine is misconfigured with any of the many possible incorrect swaps, then this test deck on that machine will give an incorrect vote total, either because any incorrect mapping would either cause a swap of candidates with different vote totals, or would cause at least one overvote, an overvote in at least one contest and at least one ballot. And it's also, at least in this case, we observe, right, you get this rigorous deterministic guarantee without any additional ballots. So I want to shift now to many of us, actually, the fun part, which is on the technical side. How do we have how can one come up with an algorithm for finding such test decks? So I'm going to spend the next chunk of time on that, and then I'll conclude by showing, in context of thousands of ballot styles, real-world ballot styles, how this algorithm compares both in running time as well as lengths of test decks compared to current practice. So, as I said, shifting now to stating our problem and approach a bit more formally. So, what is our approach to designing test decks? So first, let me specify the input to our approach. So the input consists of three things. The first is a set of contests in the ballot style. By ballot style, I just mean, you could think of it, if you're not familiar, the space is just like the election. So what are the different contests, whether that be ballot measures or candidate contests or whatever? The input includes the set of candidates within each of the contests. And finally, it includes the maximum number of candidates that a voter is allowed to select in each of the contests. How many can you vote up to? Markings can you select? So given this input, we obtain a test deck by solving something that's called a robust optimization problem. This happens to be as a professor, like what I do research on, this class of mathematical optimization problems. I'll explain why I use this robust terminology in a moment. So here is the optimization problem we solve. And I know it's a diverse audience, so I'm going to spend just a few minutes breaking down how you interpret the mathematics here. But the big picture is, this is an optimization problem that by solving it, we obtain a test deck. So let me walk you through it. So an optimization problem, right? The goal is, in one of these mathematical optimization problems, is to find decision variables that are feasible and achieve the minimum cost. So what are the decisions in this optimization problem? So there's two types of decisions. The first decision is an integer b, which denotes the number of ballots in the test deck. And b shows up here in our objective. Our objective in this optimization problem is to find a test deck with the minimum number of ballots. It's to minimize b. The other decision variables in this optimization problem are the candidates to select in each ballot in the test deck. Namely, we'll let beta 1 through beta b each be discrete sets, just basically binary sets that include a 0 or 1 variable in essence for each target on each of these ballots that denotes whether or not we're going to select that candidate. We're going to mark it, that is, in the test deck. So just a reminder, capital B, number of ballots in the test deck. Beta 1 through beta b are for each of the ballots in the test deck, which candidates should we include a vote for. So those are the decisions in this optimization problem. We will have a constraint in this problem for every sigma in this set, capital sigma, and this is what we call an uncertainty set. So in other words, this optimization problem has many constraints which are parameterized by these lowercase sigmas. And this type of an optimization problem is what happens to be called a robust optimization problem. And let me elaborate a bit. So capital sigma is the set of all bijections from targets to candidates that are incorrect. More specifically, if we let this n be the set of denote just the set of all the candidates on the entire ballot style, as well as the set of all the targets next to each of them. Then we say that sigma, a mapping from targets to candidates, is a bijection. Well, a bijection, right, means it's a one-to-one mapping correspondence. And we say it's a bijection in the set if there exists at least one candidate that does not get mapped to its own target. So I'll repeat, capital sigma is the set of all bijections that for which there exists at least one candidate that does not get mapped to its own target. And we have a constraint in this optimization problem for every incorrect bijection, every sigma in capital sigma. And what are the constraints? What constraints do we have for each incorrect bijection? Well, let T star, let me explain what these are. So let T star denote the vector valued output of a voting machine that operates correctly. What do I mean? So going back to our previous example, that simple test deck, if the beta 1 through beta B, if our decisions of which ballots targets to mark corresponded to our old test deck from before, then T star of that test deck would be equal to 1, 2, 3, 1, 2. Because if it was fed to a machine that operates correctly, it would give one vote, interpret as having one vote for the first candidate, in this case Washington, 2 for Jefferson, 3 for Lincoln, 1 for Webster, 2 for Clay. So T star is the output of that test deck beta 1 through beta B if the machine operates correctly. And T sigma of beta 1 through beta B denotes the vector valued output of a voting machine with an incorrect bijection from candidates to targets. So in other words, just to repeat, and again, please raise your hand if any of this is unclear, but just to zoom out, this optimization problem has a constraint for every incorrect mapping bijection from candidates to targets. And for each incorrect mapping between candidates and targets, it has a constraint that says that your test deck must give an output under a machine with that incorrect bijection mapping that is not equal to the correct one, which in other words means that the poll tape has to be wrong. So in summary, the goal of this optimization problem is to find a minimum length test deck such that the output of a voting machine with an incorrect bijection will be different from the output of a voting machine with a correct bijection for all incorrect bijections. It's a bit of a mouthful, but that's our goal. This is just mathematically stated the problem we wish to solve. Okay, so how do we solve it? So what we've developed is an exact algorithm for solving this problem, meaning it will provably give the optimal solution, a feasible solution that with the provable minimum cost. And before I get into any of that, before I get into how does one even go about solving a problem like this, I want to focus on the fundamental challenge with this particular optimization problem, and that is its size. In other words, what I want to talk about is how would you even how many bits, let's say, does one need to actually represent this optimization problem in memory? To answer that, let's think about how many constraints there are, practically speaking, in this problem. So we observe we have a constraint for every incorrect bijection. So for every element of this set we called capital sigma. So what is the cardinality of this set? How many incorrect bijections are there? Well, if we let n denote the number of candidates in the entire ballot style, so sum up the number of candidates in each of the different contests, then the number of bijections between n and n we recall is n factorial. And so the cardinality of sigma is n factorial minus 1. Why minus 1? Well, because that set sigma, capital sigma, doesn't include the correct bijection, right? So what's the issue here? Well, in real-world elections, n could easily be 100 or more. And so for a ballot style with, let's say, 100 candidates, this optimization problem would have around 100 factorial constraints. It's about 10 to the 157 constraints. That's much larger than the estimated number of particles in the universe. So for frequent sizes of elections, it's impossible to even just represent this optimization problem in memory, let alone solve it. So I mentioned, though, that we have an algorithm that's practically able to solve this. So what is the high-level algorithm? The algorithm is based on a principle from mathematical programming called the cutting plane method. It's a very natural idea, and it goes as follows. So we start, let me just draw your attention to this leftmost part of the circle. So in each iteration, it's an iterative method. And in each iteration, we start with a small subset of all of the n factorial minus 1 bijections. So we start with just a handful, small number of bijections. We denote that subset by sigma hat. So let that be some subset of the set of all bijections. And in each iteration, we first compute a minimum length test deck that would detect all of the incorrect bijections in that subset, capital sigma hat. And that, if sigma hat is small, that's at least small enough optimization problem that we could fit it into memory. So we solve that. That then gives us some test deck. Now that test deck is guaranteed to detect any of the incorrect bijections in our subset sigma hat, but it may not detect all possible bijections. So what we do then is we solve an auxiliary optimization problem to find a swap. A swap, by that I just mean an incorrect bijection that would not be detected by our current test deck. So we find at this stage an incorrect bijection that would not be detected by the current test deck, and we then add that new bijection into our running set, sigma hat, and repeat. So in other words, at every iteration of this method, we find a test deck that's feasible for a subset of our constraints. We then find a constraint, equivalently find an incorrect bijection that's violated, that wouldn't be detected by our current test deck, add that incorrect bijection into our running subset of incorrect bijections, and do it again. Because there's a finite number of incorrect bijections, this algorithm will terminate after a finite number of iterations. And so this is a procedure by which one can obtain a test deck. Well, in principle, sure. But so hopefully this high-level idea is clear. So why might this work well? Well, it's only going to work well if it doesn't take a huge number of iterations, right? And actually, let me be clear about the termination criteria. So we terminate this procedure once we have a test deck and we are unable to find an incorrect bijection that would not be violated, that would go undetected by that test deck, right? Because if none of them exist, we clearly have a feasible test deck for our true problem. And because this was solved with a subset of the constraints, it must have the optimal objective value. So, okay, so the punchline is, in practice, this method works on large scale sizes of real elections, terminates often within 100 iterations. And so this ends up being extremely practical. And the reason we're able to get this to terminate so quickly is because of a combinatorial property of that really it's like a theory that we've developed for characterizing a good swap, a good incorrect bijection to add in each iteration. Let me just preview what I mean by that. At every iteration, when we have a test deck that is infeasible for some of the constraints, there's going to often be many different incorrect bijections that would have been undetected. And so we have many possible choices of which incorrect bijection to add into our subset. And so what we've developed is a combinatorial theory for deciding which out of all of the different swaps that would be undetected should be added, as well as a really compact algorithm for finding such a when to add. So let me elaborate what I mean by all of this. So here is our intuition for generating high quality incorrect bijections in each iteration. And again, when I say high quality, I mean they lead to the algorithm terminating quickly. And this is, by the way, going to be, when I say quickly, I don't mean that theoretically, but like in some sort of worst case sense, but practically in a fast and for a theoretical reason that I'm explaining. Melissa, please.
What the answer is, but if you just pick a random constraint or something like that, like do you do badly, or like did you test to see, like, is it important? I'm assuming you did.
Yep. It'll be the difference between solving this in seconds and years, based on our estimates. We did this on smaller scale examples, and it would take on our first version of this, which was using random, it took hours for a pretty small example. I think it was like 20 candidates. And then with the procedure I'm about to show for generating them, it took like a couple seconds.
Cool, thanks.
So okay, here's the intuition. Let's suppose we have an election like this, consisting of 5 contests. So here we have a ballot style. These are the 5 different contests, different combinations of numbers of candidates and how many you can vote for. And let's suppose this algorithm I described has been running for a little while, and at some iteration found a test deck, and then found this as a bijection that would go undetected. In other words, suppose we're at some iteration, we had some test deck, and let's suppose that the test deck would have not detected this incorrect bijection, namely one that swapped this yes in contest 5 with B in contest 1, did this sort of cycle of 3 different swaps here, and so on. Let's now, from this bijection, construct what I'm going to call a contest graph. So more formally, let a contest graph be defined from an incorrect bijection as an undirected graph that has a node for each contest and an edge between 2 nodes if the bijection caused a candidate from one contest to be swapped with a voting target from another contest. So this is the contest graph corresponding to this incorrect bijection, right? There's an edge between contests 1 and 5 because there's swaps between them, and there's edges between 4, 2, and 3. Now, I'm going to introduce a definition. We are going to say now that a bijection is minimal if the corresponding contest graph has a single connected component. So here, this contest graph is clearly not minimal because it has 2 connected components. And here is our theorem stated informally. So our theorem says that minimal bijections are always preferred to non-minimal bijections from the perspective of eliminating the greatest number of feasible test decks. In other words, here, either of these are preferable to this. This is preferable, both of these two separately are preferable to this. Let me actually say slightly more formally what I mean by this theorem. The way we can evaluate, while we can't say anything about total number of iterations our method will take, what we can say theoretically is how many feasible solutions you're removing from your restricted problem, naming your problem with a subset of the constraints. We prove that if you have an incorrect bijection that would have gone undetected and it's not minimal, then, and you compare it to that same incorrect bijection, but where you just remove all but one of the connected components, then that minimal bijection will eliminate at least the same set of test decks from the problem we wish to solve, but may also eliminate more. Said another way, it's like in a Pareto sense, always better to choose a minimal incorrect bijection from a non-minimal one. So what's the intuition here? The intuition here is that the simpler the attacker is, or let me say it conversely, the more complex an attacker is, the less test stacks you can eliminate. Because if it's a really simple way of doing swaps, then it's going to require lots of the more complicated ones. How do I say it a different way? When it's a really complicated type of swaps like this, you can sort of overfit in the sense that like it will only eliminate test decks that really in particular satisfy all of these sorts of things. Whereas when it's really simple, you get to eliminate the most. Now, okay, fine. So we have some desirable property of incorrect bijections, but how do we actually find one? And the answer comes from solving a variant of a min-cost network flow problem. So theorem, a minimal bijection that's undetected by a given test deck, if one exists, can be found by solving a mixed integer linear program with only O of n squared binary decision variables, n here being the number of candidates, and O of n plus BC constraints, B being the size of the test deck that was found in this current iteration, and C being the number of contests. And this is this mixed integer linear program that is very close to a min-cost network flow problem. Let me explain. So the decision variables in this problem we denote by xij. So xij equals 1 if and only if candidate. By the way, how are we doing on time? Because I actually don't need to go through the details here for.
Maybe about 10 minutes before questions, or
okay.
Up to 10 minutes.
In that case, yeah, I'll explain it high level without the math. The basic idea here is this is an optimization problem over a bipartite graph. On one side, you have candidates. The other side, you have targets. A bijection is clearly a matching between the nodes on each side. This optimization problem, which can be solved in like essentially milliseconds most of the time by state-of-the-art mixed integer linear programming solvers, aims to find a bipartite matching, so matching from every candidate to every target, that does not swap. So this xij equals 0 means it does not swap or connect a candidate and a target that receive different vote totals in your test deck from the current iteration. And this constraint here, and this is the only constraint that makes it not a normal network flow problem, is that we have a constraint that the xij's cannot induce the mapping cannot induce an overvote in any of the ballots, in any of the contests. But this problem, and in particular, the objective is to minimize the number of non-identity swaps. In other words, the number of matchings that are not from a candidate to its own target. And one can prove that this problem is guaranteed to output a minimal bijection. And so, zooming back out, at every iteration, we solve some other problem to find a test deck that's feasible on our subset of the bijections. We then solve this really small scale mixed integer linear program to find a swap, a bijection that would go undetected by the current test deck if one exists. And moreover, this small problem here is guaranteed to give, out of all the bijections that would have been undetected, find one that's minimal. And that is what, as I alluded to in answering Melissa earlier, solving this versus picking one at random. And by random, we actually even have to define exactly how you randomize over that space. But in the way we did it led to this extreme speed up. And that's what makes this thing actually practical. So let me just show how this approach scales to real-world elections. So we've been working in collaboration with the Michigan Department of State over this past year and a half. And so what I want to show is some numerical results from their that we did retrospectively with them on their November 2022 election. So in that election, across the state, there were just under 7,000 different ballot styles, different actual ballots that people saw. Why is that the case? Remember, local school board is different in every town, right? So there's lots of different ballot styles people see. In this election, there is on average about 30 contests per ballot style, and on average around 100 candidates per ballot style across the contests. So under Michigan's current practice, there are test decks which satisfied that requirement that every candidate within a contest must get a different number of votes. Applying their current practice in that election, on average, their test decks would require about 22 and a half ballots. So just a reminder that under their current practice, they are guaranteed to detect swaps within contests, but not across. Applying our approach, on average, the test decks obtained by our approach require only about 22.8 ballots per test deck on average. And our test decks detect swaps both within and across contests in a mathematically deterministic and guaranteed way. Computation time, applying this this combinatorial idea of how to choose what swap you add at each iteration, we're able to do the entire state at the time that we wrote the paper, just under 7 hours. Now we're down to, I think it might be less than an hour. Applying just some clever, like theoretically justified ideas in different places. And I should note here, like I'm trained as a theoretical computer scientist. Like everything I've shown here is obviously like not polytime in a provable sense. Although anyone who likes computational complexity, if you're interested, please talk to me because there's a bunch of questions here related to like approximability and complexity stuff at various parts here that we don't know the answers to. Skipping that one, this plot I just wanted to shows the time. So every dot here shows one of the different ballot styles. The x-axis shows the number of iterations it took our algorithm to converge. And the y-axis shows the total amount of time it took for the algorithm to run. And I plot this in log-log scale. And so this is like a polynomial here. And so this plot show that, well, first, before even looking at this line, we observe that most of these points for most ballot styles ran in less than 100 iterations. And moreover, the computation time is really closely just a function of the number of iterations. Empirically, the computation time scales about quadratically, just over quadratically with respect to number of iterations. Hence why being smart about how you decide what swap to add in a way that reduces number of iterations leads to such a significant decrease in computation time. I'm going to skip through that. So the real world impact here. So this approach was piloted successfully in a few different 2023 Michigan elections. And then we've been working with Michigan to help them deploy it statewide November of this year, as well as talking to some other states. And with the remaining like 2 minutes, I just want to describe how we're actually deploying this at scale. So elections are in states like Michigan and many others as well are highly decentralized within the state. Precincts and counties operate as sort of independent entities. And one of the big challenges for the state is just knowing what's on the ballot. It's hard for a state to know what's on the central Department of State to know what's on the ballot in each of the different places accurately. And obviously to apply the sort of mathematical optimization algorithm, you need to know what's going to be on the ballots. So what we're developing is basically a website that county clerks or election officials can log into. They log in, they can upload a PDF of their blank ballot. We then run our algorithm, and then the clerk can download the output, which in the form of a pre-marked test deck PDF. So they could just give it to a printer if they want, or just shows them how to do it by hand to print their test deck, as well as a test deck chart, which shows them, if they're doing it by hand, exactly how to mark it, as well as what the output totals should be. And one of the nice things here is that we've already open sourced the code for checking whether there exists a bijection that would go undetected. So even if you don't trust our website, you don't trust anything in elections, but you go the day of LNA testing in person, right? That thing that we do pre-COVID days. But so all right, you go your actual observe an LNA testing, and you can put in see the test deck they're physically using, and put it into our open source code to check whether it indeed has the security guarantee that we say it should. And so it's open source, so you can even check that code yourself. And so that's how you can trust that and independently verify that the output of the website is correct. So in summary, our approach offers a practical, rigorous way to detect an important class of voting machine misconfigurations before elections take place. I want to just quickly note, there are many, many ways that voting machines can go wrong, that there can be issues, either deliberate or accidental, in the vote counting process. What I presented today makes absolutely no attempt to cover the vast majority of them, but rather allows us to identify before elections as one type of misconfiguration that have occurred accidentally, may be able to be deployed maliciously, and have caused real issues in practice. And in particular, our approach just requires a simple modification to what states are already doing in form of their testing. Michigan's successfully piloted it, planning on deploying it statewide. And I hope, now just speaking about my area of research, that this work showcases how techniques from my field of operations research, mathematical optimization, can be used to improve the security, increase public confidence in elections. That I'll conclude.
Thank you, Brad. So I'm going to start off with comment and question, if you don't mind. First of all, there's a lot here that I find so counterintuitive and surprising that my intuition would have said make complex changes to iterate that would have been more efficient. Also, I hadn't seen any min-cut max flow stuff since I was an undergraduate. That it comes in here surprises me a lot. I'm wondering how much have you considered or looked at sort of broadening the class of things which your approach can handle, like maybe misconfigurations that aren't a bijection but map two targets to the same candidate, or misconfigurations where a contest is marked as vote for up to 3 when it's really vote for up to 1, and therefore an overvote is not detected, because as I saw, you are very dependent on using overvotes as one way of detecting a bad bijection. So have you looked at any of those things?
All to varying degrees. So let me break apart into the different things that you said, and I'm going to do it in reverse order. So the last thing you mentioned was, what about checking for things such as whether the machine has been misconfigured such that the vote for up to numbers are wrong. So many states have that actually as a legal requirement, that you must include a test deck that includes the maximum number or variance thereof of the number of votes, or do a 1 over in contest to make sure it counts it. So we, when we run this in the wild, actually impose that as a constraint. So we say, not only does it need to have a test deck with just these properties, but we impose that actually the first ballot we hard code what its values must be to ensure basically giving a 1 over in different contests. And we do it in such a way, and then we say to the algorithm, this is an additional constraint you need to satisfy. And one of the magic things about mixed integer linear programming is you can do that. You can add in constraints like that and still apply the same method. So for that last part about what if, here's another example. What if, so you want to have a ballot that checks if there are targets elsewhere like, let's say there's maybe just at the corner of the page being interpreted as a target. Like, that's a concern, right? Because if an attacker is changing around the XY coordinates of where it's looking for the target for a given candidate, who says it needs to be restricted to actual bubbles, if that makes sense? So another thing that we have is we have a ballot that in Michigan, they call this stray mark ballot that must be black everywhere except for the targets. And this actually works in that framework because you just treat that as another candidate, right? And then it just still builds a framework. So what is my broader point? My broader point in addressing the last half of your question is our framework is such that in this sort of tool of mixed integer linear programming is such that you can add these sort of one-off, odd, irregular types of constraints in and just pass it off to these solvers that have been improved drastically over decades. So that's the second half of your question. Now to your first half, which is, are there other classes of threat models that one can consider or should consider? So the reason, before I answer that, the reason we focus on not these bijective mappings is these are ones that we feel are hard for a well-implemented machine to be able to detect offline. What do I mean by that? Well, if someone is just changing the configuration of the machine, but not the machine itself, right? There should be sanity checks in place that check for things like 2-to-1 mapping, like two targets going to one candidate. It might occur sometimes in real life, like maybe multiple parties, a candidate's listed under multiple parties, but there are certain checks machines should be able to do. And so but you can't really do a check for the XY coordinates in a similar way. So we thought bijections were a very reasonable and realistic place to start. Now, all that being said, what else could there be? So one-to-many or many-to-one mappings are stuff we started playing around with. And the question then becomes, how much additional can you detect without making the test deck become too long? That's motivated us to think about randomization. So if you allow there to be randomization in the way you generate test decks, can you start covering in some probabilistic way much broader classes of things while still maybe having these more what we've already established deterministic guarantees? This is like a wonderful question. How do you even think about doing that theoretically in a sound way that is on our list of things to look at? And we would love anyone, you or anyone else here who's interested in this sort of thing to join us. Let me just add my favorite special case that's low on our list, but would be fun. In Hawaii, maybe in other states, but at least in Hawaii, they allow political parties to come up with their own test decks. So there, like the Democrats get to come up with a test deck, Republicans get to come up with a test deck. And so there becomes the interesting question of, if you only want a test deck to make sure your own party isn't being screwed, sorry for the language, how would you design a test deck? So you could have a lot of fun with different variants, but ultimately it comes down to what is the right threat model given really what we really love to do is to go into each individual vendor's machines and understand based on how they're coding. Of course, as you know, Josh, you can't actually usually get to that. But if we knew what checks they were doing under the hood, whatnot, you could design an uncertainty set that sets sigma to correspond to it. So those are some of the things we've been thinking about.
Great. Well, lots of interesting questions there. Any other questions in the room? Yeah.
So I have a question, which is like, I kind of think about this. So trying to minimize the number of the ballots in the tech stack, so the assumption I think here is like you only run the test once. What if you run a shorter test but twice, for example, or multiple times, and you need to make sure all the tests pass. So now for each test you can run like a much smaller size. Then the total size might even be smaller. I don't know, it could be larger, it could be smaller. Is that possible?
So it could be much smaller. So just to repeat the idea, let's take that idea to an extreme. Let's suppose after each ballot, we could see how the machine interpreted it. In that case, it actually becomes very simple how to do this. You just basically make sure that on every ballot, you could, hopefully quickly convince yourself that you could actually figure out, because you get way more information, so you can get by with a lot fewer ballots. So why not do that? Turns out practicality. It can take a very long time to actually for the machine to print this out. And then the official has to reset the machine. And from talking with officials across at least the state of Michigan, but similar machines elsewhere, basically election officials, people who do this, have told us no way. If you do more than a couple test decks printouts, they're not going to do it because it's too different from current practice. It's too time consuming, and it just becomes a pain in the something, right? And so that was one of the considerations here, is to try to keep it basically how everyone is already used to doing it. The philosophy being, if we can get a lot of gain from not any very minimal more work, then it's a win for the country. I will say though that even if one came up with was able to do something like you described, in states such as Michigan, we're already matching essentially what the minimum number of ballots would need to be under their current practice. So unless they also change the laws in the state, like we're essentially can't get by with less in a way that satisfies their legal requirements than what we're currently doing. But of course, that doesn't apply to other states. Marsh?
Yeah, so let's say you have the provably minimal test deck to test all errors. Would you ever just add some random ballots in as well for good measure?
So it's an interesting question. So the question is, what do we mean by good measure? So the guarantees are the test decks
Superstition.
Well, so it comes down to what I'm not sure how to respond to or how much value is right to put on superstition. What I'll say is the following. I think there is a tremendous value in having deterministic guarantees, particularly in elections when possible. Why? Well, what we don't want is for some, conspiracy theorists after your election to say, well, no one has a guarantee that this thing was detected. We only know it probabilistically. This wouldn't have been caught by whatever you use. Now that actually isn't even the biggest concern. The biggest concern with randomization is that, let's suppose we had some RNG, used it, came up with a test deck, then the test deck got used in practice. There is theoretically a time in between the RNG was determined and the test deck was applied that an adversary could modify a machine then in such a way that would allow it to not be detected by that realization of your random number generator. Now, all of that is just to say that I think there's just really value in the deterministic way that we're doing it. Obviously, determinism isn't always feasible in all places, but I think that's kind of my
So
view.
could a bad guy add ballots that then undo the tests?
So let's suppose a
in the
bad
main
guy
thing.
did that.
Good.
Good. So
Got it.
let's suppose someone hacked our website, or the website wasn't hacked, but then that afterwards they modified it. Now comes testing day. Someone has to show up, the official, with the physical test deck, and we have an open source checker to see if it gives the guarantee. So you can, at the date, like literally right before it's run, independently use the code that's open source and check if it still has a security guarantee. Now, it may not be the shortest at that point, but I feel like it'd be strange for someone to hack it just to add ballots, but still keep security guarantees. I'm not sure what anyone's incentive would be for that, but anyone can independently on testing day using the open source code check whether it still has the guarantee. Melissa?
Yeah, so I guess I was wondering how close to in the example you came up with that you had this minimal deck that basically satisfies the initial constraints. It looked a lot like your initial setting. You just move things around, right? So the same size and also super easy to check that each candidate got the same number of ballots. How close do you get to that in your optimal solution? Is it close to the same number of ballots they would have gotten from the old technique, or is it sort of human verifiable, or is it just I guess that's the question.
So let me go to my first backup slide. Here it is. So this plot shows you're fantastic. This plot shows for the Michigan 2022 elections, the difference between the current practice and optimal and the Wensmore algorithm on a per length basis. And let me tell you what I mean by that. So in this plot, the green bars show how many ballot styles there were where the under their current practice would have had the given test deck length. So by that, I mean, under their current practice, just over 6,000 of the ballot styles would have required 21 ballots. on their election. Out of I don't remember how many this is, maybe 100 or two of the ballot styles required 23 under their current practice, and so on. And the red shows how many ours would have required. And what you basically see is, and up here shows the difference, the change in how many ballot styles. What this shows, and actually what can be verified, is that nearly all of the ballot styles from this particular election in Michigan required no more ballots under ours than theirs. It just required scrambling them in a similar way from before. For those that did require additional ballots, it basically always happened when you had a very small number of ballots to begin with. And we observed through doing further investigation is that there was actually a common property among all of the ballot styles for which ours was longer than current practice. And that was in cases where there was a large number of what are called non-competitive contests, where a non-competitive contest is a contest in which you can vote for up to the number of candidates. It might seem strange that it exists, but it shows up in cases like judges if you're just voting whether to retain them. There's no, it's only a yes. So you can vote for up to number. And when there were a lot of them, those were the cases where our test decks were a bit longer. And the reason for that is a bit subtle, and it has to do with certain properties that in order to have our security guarantees, you have to give it. It doesn't matter. The point is that explains the discrepancy. So the answer I just gave was to the aspect of your question regarding lengths, like when do the lengths differ? In all cases, though, ours are a bit scrambled. They're a bit scrambled because they kind of have to be in such a way that induces those overvotes everywhere, such that no matter how you sort of swap things around, it either swaps candidates with different vote totals, so that part stays the same, but you need to make sure that different combinations of candidate votes show up in different places such that when you swap any sort of combinations of them, an overvote must occur. And so from that perspective, it is a bit more complex. Practically speaking, that is a factor to consider if someone's filling out test decks by hand. If they're using a printer to print their test decks on their behalf, it's less of a concern. But length still matters of number of ballots just because it costs money.
Did you think about
Does that answer your question?
An extra, secondary optimization goal of simplicity of the ballots, or fewest number of votes total, or human?
In fact, we do that. Yeah.
Okay.
So we have a little way of doing it, which is we sort the candidates based on so that in every contest, the first candidate within that contest is going to be the one that gets the fewest number within that contest. The second, so on, just so it looks aesthetically similar to the original. Now, your question, I think, is a fascinating one, which is what factors really go into the time it takes for people to fill these out? And can we include those factors explicitly in our optimization framework? The answer is surely yes. It just comes down to characterizing in a quantitative way what it means for a test deck to be simple. And I just don't, we have our senses of it and we've talked to people, but we haven't done it in a scientific way, figured out what those factors are. It's a wonderful question.
I guess I'm also thinking I don't know, Fahrenheit vote worker who says, I don't trust any code, I want it to meet the old requirements. The old thing looked pretty easy to check. You just count, you have 1, 2, 3, whatever, everything's, presumably you can always do it where they're all sequential. So I guess I was wondering if there's simplicity of if you wanted the human to verify, at least the old constraints were which I guess would be slightly different than total number of votes or challenge of filling them.
Good. So so you could still do that. Indeed, the contests are so ordered so that the first candidate receives the fewest number, then the second, then third within each contest, and you can manually go and compute the totals. And in fact, it's a good standing check to do that because it's an easy thing to check. So in other words, you can easily verify as a human that it will detect all swaps within contests. The thing is, there's just way more that go across contests.
Yeah.
And for any particular one you might come up with, you can verify it. You can look to see, is it, if in a test deck, either swapping candidates with different vote totals or going through each ballot, can you find, is there at least one contest and at least one ballot that then gets an overvote? So for a particular by incorrect bijection, you can manually verify it. It's just there's a ton of them.
Yeah, it sounds like the current constraints are trivially verified as long as each candidate within a contest has a different total. And
Yes, and
that's
we prove
done
that.
by hand.
Yep.
Right.
There's other simple things you can do by hand, such as if you have, I don't know if I want to. I'll say brief. Suppose you have two choose one contests, meaning there's two candidates, you can vote for up to one. It must be the case that they don't both get the same numbers for the first and for the second. In other words, if you have, let's say, two ballot proposals, each are, should we add amendment proposition 7.31 whatever to the state constitution. Suppose you have two of those. You can't in both of those contests give one vote for the yes and two for the no. Or you can't in both give 2 for the no's and 4 for the yeses. Like it can't be the same in both, because otherwise you could just swap the entire contest together. And so we have a mathematical property that we call lexicographic ordering of contests that says that, and this you can easily check by hand, are all contests of a similar type, meaning same number of candidates and maximum number of votes, are all of them having the same totals for their candidates. And if not, then you can't do a simple swap of contests. I don't know if that made sense, but that's another thing that one can visually check.
Thanks.
Anything else online? Yeah. I think great talk and some really good questions. So thanks a lot once again.
Thanks again for the invitation. Our paper's online, and please don't hesitate to reach out if any of this is interesting to you, because especially if you do algorithms, you do anything with approximations, randomized algorithms, complexity. There's plenty here that we would love to chat about. So thanks again.